Let's have a look. So we are looking today at sine, cosine, and tangents again. And our goal today is to look a little bit more at the unit circle and just look at some of the ways that we can use the unit circle to determine sine, cosine, and tangent values. We want to focus a little bit on radians as well, of course, for today's lesson. So a little reminder of last class. Make sure you know this vocabulary. So the vocabulary comes up quite a little bit. A ray in so if we start with the measure of an angle is the ray in standard position. So this is what we call the initial ray. We call this the initial ray. So the initial ray, and here at this point, this is the vertex of the ray. So this is the vertex. So when the vertex is placed at the origin and the initial ray is placed on the positive x-axis, we say that the angle measure is in standard position. We could have the same angle not in standard position. So for instance, we could have the same angle could be given like by these two rays here. It would measure the same angle as the one that we're looking at, but it's not in standard position. So standard position requires that the initial ray is on the positive x-axis. When we rotate that ray around to some other location, we call this one the terminal ray. We call this one the terminal ray. This gives us the measure of an angle. So it gives us the measure of an angle here, like this. So when we place an angle in standard position, let's say that this angle is 120 degrees. Let's say, for instance, for sake of interest, so e.g., the angle measure, the measure of the angle equals 120 degrees. How much would that be in radians? How much would that be in radians?
2 pi over 3.
Nice one, Sam. 2 pi over 3. How do we convert? One of the key things for conversion between degrees and radians is to remember this point here. The terminal ray is here. The terminal ray is here. How many degrees have we rotated by? If the terminal ray is here, this is 180 degrees. How many radians is that? Pi. This little factoid here is very useful to remember. And we can use this for doing conversions. So when you're doing for conversion, you're either going to times by 180 over pi, or you're going to times by pi over 180. And this is how I remember. In order to convert from degrees into radians, you've got to cancel the degree symbol. The degree symbol has to disappear. So the measure of the angle in radians is going to be 120 degrees. Now we're going to have to multiply it by this, such that the degree symbols cancel as well as the numbers. So you're canceling the degree symbols as well, which is what causes the unit conversion. This is going to give us, I think Sam told us it was 2 pi over 3. This angle here would then be that. Are there any other angles that could have its terminal ray in standard position in the exact same place? Mohammed? You could rotate anti-clockwise. Good one. So let me just clean this up a little bit. So what Mohammed is saying is you could take the ray from this position and we could rotate it round to here, and we would still end up in the same position. This would be an anti-clockwise. That's an awful error. I'm going to do it again. There we go. That's still not good, but it's good enough. How many radians have we rotated now?
Negative pi.
Not quite. Not quite. So firstly, the good thing that he suggested is that we rotate by negative pi. So if we were to rotate by negative pi, that's going to bring us to there. So negative pi here. How much is this rotation here? In radians. This one is a negative pi over 3. So this angle measure could also be negative pi minus negative pi over 3. To do the arithmetic here, if you're converting pi and adding it to other fractions, so remember that pi is also 3 pi over 3, 6 pi over 6, 5 pi over 5. So convert your pi's into using this way of expanding it. So we get, for our pi, we get minus 3 pi over 3, minus 1 pi over 3, all over 3. How many pi's do we have?
Minus 2 pi over 3.
No. Minus 4 pi over 3. Excellent. So we would have minus 4 pi over 3. And that lands us in the same position, because what we see here is that positive angles are counterclockwise rotations, whereas negative angles are clockwise rotations. Are there any other angles that could have the terminal ray in the same position? Are there any other angles that could have the terminal ray in the same position?
You could add 360 degrees.
If we were working in radians, we couldn't.
You could add 2 pi.
So Sam is correct. Sam suggests we rotate a full rotation first, bringing us to 480 degrees. But then 360 degrees is how many radians? 2 pi. So we can add 2 pi to this. In fact, we could add any number of 2 pi's to it. So we could have any number of 2 pi's to that rotation, where n is a member of the set of integers. So we just keep rotating round and round and round and round. Any questions? Mohammed? Sorry? Yeah, let me zoom in on this notation here. So n is an element of the set of positive integers. So the double stroke z is positive integers. No, sorry. What am I saying? It's not positive integers. It's integers. If we wanted positive integers, we add a little plus here. So this is the set of integers. So any whole number, so any whole rotation of the circle. All right, measuring angles. So the way that we measure angles on this course is by looking at the arc length here. So we can look at the arc length here, and then we can divide it by the radius, and this will give us the measure of the angle. This will give us the measure of the angle. So if we wish to find out how many radians are in a semicircle, so remember that the circumference of the circle is 2 pi r. 2 pi r. So the angle measure, the measure of the angle in a semicircle, what is the circumference of a semicircle? Pi r. Why? Because it's half of a circle. And if the circumference of a circle is 2 pi r, half of that is pi r. So the measure of the angle in a semicircle is going to be pi r divided by r, which is pi. What about in a quarter circle? The measure of the angle is going to be a half pi r over r. So pi over 2. This is equivalent to 90 degrees. All right, sectors and segments. So for instance, when we define, this is how an angle is defined. So it's a measure of the length of the arc divided by the radius. And that's why 1 radian is defined. Yeah, the circumference of a sector divided by the radius of the sector. So what is a sector? Well, a sector is this, basically. So in standard measure, if you look at this, this is your initial ray, and this is your terminal ray, and then you define a sector like that. An arc is a measure of the circumference of a sector. We can have a couple of formulas to show that the arc length is going to be equal to theta r. Let's do a show that of this one. So the left-hand side is equal to the arc length L. So the arc, how do we find the length of an arc? If we have an angle, here, theta, how does that define what fraction of the circle we have? How does that angle define what fraction of the circle we have?
Don't you put the degree of the sector divided by 360?
If we're working in radians?
The degree of the radians of the sector divided by the 2 pi.
So this is going to be, this little bracket here, that's what fraction of the whole circle is the sector. So what was suggested firstly by John was this. This is what fraction of the whole circle is the sector in degrees, and then we convert it into radians. Now, what is the whole arc of a circle? The circumference. What's the formula for the circumference? 2 pi r. 2 pi r. So if we simplify that, this beautifully cancels. And we end up with theta r, which is the right-hand side. All right, show that the area of a sector A is a half r squared theta. So we'll do the same approach again. The left-hand side is going to be equal to area, which is equal to some fraction of the circle multiplied. What's the area of a circle? Pi r squared. What cancels this time? Just the pi's. This gives us a half r squared theta. Oh, my theta is rubbish. Which is equal to the right-hand side. All right, take a note of these two formulas. You're going to use them.
So you think you could formula, could you just put r squared theta divided by 2?
Same.
Okay. You want to put it in the formula?
We recognize no difference. We recognize no difference. All right, make a note of the two formulas. Have a go at these two questions. All right, let's have a look at our two questions. So for question A, the arc length L is equal to theta r. Our angle is 3 pi over 4 times by 8. That's easy. 6 pi centimeters. B. The area is going to be a half r squared theta, which is a half r is 8 squared times 3 pi over 4. Now that's going to be 8 squared times by 3 pi over 8. Well, that will cancel one of those. We get 3/8 of 24. 24 pi centimeters squared.
How the arc length of A is 6 pi centimeters, the circumference is 2 pi.
Because the radius is more than 1. It's 2 pi r.
Oh, so the circumference would be 2 pi times 8.
Yeah. It would be 16. It would be 16 pi. It's a dilation. All right. Unit circle. Oof, okay. So, unit circle here. Let's have a look at this. Our goal here is to look at in which quadrants the sine and cosine values are positive and negative. So firstly, we have, with the unit circle, the coordinates of this point P is the cosine of theta, the sine of theta. As seen previously, this vector here is the cosine of theta. This vector, let me do that. This vector here is the sine of theta in the unit circle. The slope here is equal to the tangent of theta. The slope is the tangent of theta. So, here in the first quadrant, the x values are all positive. The y values are all positive. So, let me just do this bit first. So this is the first quadrant. This one here is the second quadrant. This one here is the third quadrant. This one here is the fourth quadrant. So here in the first quadrant, the sine value is positive because the y value is positive. The x value is positive because the cosine value is positive. And the slope is positive because the line is always going to be going up. So here in this particular quadrant, all three are positive. Now, if we rotate this a little bit now, and we place if we reflect in the y-axis, the line will be here like this. Is that a line? It looks like a curve. There we go. The line will be here. Now the vector, which indicates the cosine value, will be moving in the other direction. So this means it will be minus the cosine of theta. It'll be the same length as on the right-hand side, but in the opposite direction. So it will be minus cosine of theta. Yeah. So in this direction, the vector will still be sine theta. What about the slope? Is the slope positive or negative? Negative. So the slope is negative here because it's always going to be going down. So which of the trigonometric functions will be positive in the second quadrant? Sine. Just sine. In the third quadrant now, let's reflect it down again in the x-axis this time. We end up with a line here looking like this. Our cosine value is still the same, but our sine vector goes downward like this. And we now have a minus sine theta. What about the slope? So the slope is bigger than 0. So in the third quadrant, which of the trigonometric functions is positive? Tangent. Lastly, the fourth quadrant, we go to that point there. We bring this one down. Let's use the symmetry. Our sine value is still going straight down like this. So the sine, it's minus sine of the angle here. What about the slope? Is this positive or negative? The slope here is less than 0, so it's negative. So which function is positive here? Cosine. So sometimes we use the acronym to help us on this one. ASTC. All students take calculus. It's very mathy. Mohammed. Very inquisitive today, Mohammed. Very inquisitive today, Mohammed. This is good.
So how come minus 1 don't go to the slope is based on 0?
That means positive.
Yeah, I know. But then when you said order was that you slope equals down, is that just the same thing?
Yeah, so on the first one I said that I reminded you that the tangent of the angle is equal to the slope. I didn't indicate whether it was positive or negative because in that first quadrant, I think it's pretty obvious. But people get a little bit confused in the other quadrants, whether it's positive or negative. So in first and third quadrants, that's the same line. That's the same line. It continues all the way through. It's positive. Yes.
Remember you said earlier that in your triangle where it's all reflected like the opposite? Like the triangle is like that, and the opposite is reflected like that. Is there ever a scenario where it's reflected the same way?
Not following, but we'll move on. I'll pretend it was a good question. Thank you. All right, so we need to use the symmetrical properties of the unit circle to determine the following identities. Let me do the first one for you and show you how it works. So, as you know, the x value here is the cosine, and the y value here is the sine. If we have our theta there, if we rotate round, all the way around to here, how much have we rotated by? By pi. If we then take a line, let me go like this, to this point here. So this angle here is theta. So this angle here is how much? This is minus theta. So if we rotate forward by pi and then backwards by theta, we end up with this angle here. Sine of forwards by pi, backwards by theta, that's that point there. So the x-coordinate of this one, the coordinates of this point will be minus cosine of theta, comma sine of theta. So if that's the coordinates of that point, then the sine of this angle is sine theta. What is the cosine of this angle? What is the cosine of pi minus theta going to be? Isn't it? So negative cosine theta. We can see it here. What will the tangent be? Well, the tangent will always be the sine of the angle divided by the cosine of the angle. And that will give us minus tan theta. So we've got another angle here, pi plus theta. So if we rotate to pi like that red one there, and then we continue on another theta in this direction this time, we will get pi plus theta. The coordinates of this point is minus cosine theta, comma minus sine theta. So what would these identities be? Discuss with the person next to you. Let's have an answer from Jash and Carlos. What will these ones be? Negative sine theta. Negative cosine theta. Tangent of theta. Perfect answer. Thank you. All right. How about our last one? So if we rotate from here to there, we're rotating another pi. So the complete rotation back to the starting point of the initial position would be 2 pi. From that point, if we rotate backwards in this direction by negative theta, we will create the angle 2 pi and then backwards by theta. What is the coordinates of this point here? The coordinates here will be cosine theta, negative sine theta. Use this point to find these last three values. Let's have Zane. What are our answers here, Zane?
Sine is negative.
Sine of what?
Sine 2 pi minus theta.
Yeah?
Is negative sine of theta.
Negative sine theta.
And then cosine 2 pi minus theta is cosine theta.
Cosine theta.
And then
Negative tan theta. Excellent. Excellent. All right. Okay, these identities are very useful. You need to use them all the time. You don't necessarily memorize these ones. Remember how we get them by just doing that particular unit circle diagram, and it helps you pull them off.
Sorry, I was fully memorizing the circle, but do you recommend that we memorize each little thing?
No.
Or we just know the system to get each radius?
I recognize you know the system to get these identities, that you know the exact value table, and then use the same symmetry here to reflect those exact value tables beyond 90 or pi over 2. Right. You can memorize it because it's a pattern. You can just memorize it all the way across to 2 pi because it's a pattern that goes up and then down and then a negative. And
isn't it just hard to memorize the first quadrant and then the rest you can solve for whatever?
Yeah, memorize the first quadrant, work the rest out.
That also helps with understanding.
Yeah, it does. All right. Have a go at this problem. Find the sine, cosine, and tangent of 225 degrees. I shall give you a few minutes for this one. Okay, so we need to find the sine, cosine, and tangent of 225 degrees. So the first thing we want to do for this type of question is to draw up our exact value table. So it goes 0, pi over 6, pi over 4, pi over 3, pi over 2. Then we need sine x, cosine x, tan x. Next we need to fill in our values. We got our exact value table. Now we need the unit circle. (225 degrees). 225 degrees. If we take away 180 from this, how much is left? 45 degrees. So the angle that we're after is basically going to be here. At 180 plus 45, this angle here is going to be 45 degrees. So what we do is we go to the exact value table and we take the sine, cosine, and tangent for those three values. That's here. And then are they positive or negative in this quadrant? So which one is positive in this quadrant? So it's all students take calculus. So only the tangent is positive down in this quadrant. So we are to find the sine of 225 degrees. That's going to be that's going to be negative root 2 over 2. The cosine of 225 is going to be negative root 2 over 2. And the tangent of 225 is going to be 1. Are we good?
Yes, sir. Yeah.
Right.
Is putting the table part of the solution?
Sorry?
Like if I don't put the table, would I use one?
No, not necessarily. It's good strategy. So typically if you're doing a paper on this, it's useful to have them down somewhere. It's not usually in the mark scheme. It's evident that you pulled the value from somewhere.
They wouldn't give us like a blank unit circle.
No. Alright though, so if the cosine of theta is equal to 0.5, the tangent of theta is negative, find the sine of theta and theta in degrees. Have a go at this problem. So, cosine of theta equals 0.5. We start this at the unit circle. What does this mean? So from the unit circle, we know that we have a cosine value which is positive. So it's got to be in the first or fourth quadrant. In fact, we know that the cosine value is 0.5. That's here. So if we draw a vertical line like this one, this is the line x equals 0.5. So our angle is either here or here. So referring back to the unit circle, when we have the cosine value being 0.5, that's a half, that means we have pi over 3 or 60 degrees. We're in degrees. So we know then now that this angle here is 60 degrees. So this angle here is minus 60. So it's one of these two. But secondly, we're told that the tangent value is negative. Now this line is clearly a positive slope, so it can't be 60 degrees. It means that it can't be 60 degrees. It has to be negative 60 degrees or 300 degrees. So theta is equal to 300 degrees. Now the sine of 60, let's go back to our exact value table. The sine of 60 is root 3 over 2. Now in this quadrant, the sine values are negative. So the sine of theta is going to be negative root 3 over 2. Okay, find the value of theta in the interval from 0 to 2 pi. Have a go at these two questions. 5 minutes for these ones. Okay, so Yusuf, what are we saying?
So for A, I got 5 over 6 and 5 pi over 6.
So let's do a little unit circle for everybody so we can follow along. We draw a unit circle like this. If the sine of theta is equal to a half, that means we are going through a y value through here. This is the line y is equal to a half. So the sine values are here and here. And we're looking at this direction here and this direction there. This is both a half. So the angle here at this point from the exact value table, as Yusuf says, is pi over 6. So this angle here is pi minus pi over 6. which is 6 pi over 6 minus 1 pi over 6, 5 pi over 6. Sorry, I just want to shrink that a little. Resize. There we go. So our answer there is theta equals pi over 6, 5 pi over 6. How about the second one?
For the second one, it applies 5 pi over 6 also applies to cosine negative.
That's one of the answers.
It's one of the answers.
Let's look from a unit circle perspective. Let's look from a unit circle perspective, because that's what the whole lesson is about. Let's whiz back to the goals, see what the hell we're doing today. So we come all the way back here. So students will synthesize trigonometric identities by leveraging the periodic and symmetric properties of the unit circle. We just did that. Students will identify angles in different quadrants that share the same sine and cosine values by analyzing the periodicity and symmetry. So this is what we're doing here now. So we're using the symmetry here in the unit circle, and we've got our circle looking like this. So firstly, we determine this line here like that. It's about 0.866. This is the line where x is equal to minus root 3 over 2. So our sine value and our cosine values are on these two. So the angle here, so root 3 over 2 for a cosine value from the exact value table is this one again. Root 3 over, root 3 over 2 is this one. Root 3 over 2, we've got a pi over 6 involved. So using the symmetry, what we do is we say that this one is going to be symmetrical with this one, where this angle is pi over 6. I've drawn it a little large. So this angle here is minus pi over 6, and this angle here is also pi over 6. They are plus and minus 1 pi over 6 from 6 pi over 6. That's what we've got here. This is 6 pi over 6. So plus and minus 1 gives us 5 and 7. So this implies that theta is equal to 5 pi over 6 or 7 pi over 6. Last question. Have a go at solving this one. So for this equation, we've got what's called a disguised quadratic equation. Use the variable substitution where we let t equal sine theta. Use the variable substitution and then solve for t before solving for sine theta. Give you 5 minutes for that one. All right, last one. So we're going to do this variable substitution. We get 2t squared plus t minus 1 equals 0. Now, if you remember how to solve and factor quadratics like this one, we take the lead coefficient and then we take the constant at the end and we multiply them together and we get minus 2. We then consider which numbers multiplied together that give minus 2 add together to give 1. Here, we've got a 1 there. Ooh, we've got a 1 here. So we're going to need 2 times negative 1, because 2 plus negative 1 is going to give us 1. So that gives us the different bits and pieces. We pop this in now, and we split that middle term into plus 2t minus 1t minus 1. And then we factor in pairs. So we factor out 2t from this one, and it'll give us t plus 1. We factor minus 1 from this one, it will give us t plus 1. So the complete factorization of this is 2t minus 1 t plus 1 equals 0. Resubstitute, and we get 2 sine theta minus 1 and sine theta plus 1 equals 0. Now then we need to solve each of these two equations. So one possibility is that 2 sine theta minus 1 equals 0, using the zero product theorem. So that means that sine theta is equal to a half. From the exact value table, that would be pi over 6, yeah? So a quick unit circle. A quick unit circle, and we've got pi over 6 and 5 pi over 6. So this is pi over 6. This is 5 pi over 6. So this is going to give us theta equals pi over 6 or 5 pi over 6. Now secondly, we get this other equation here, which will be that sine theta plus 1 equals 0. That means sine theta equals negative 1. Solving this on the unit circle, you need the y value to be negative 1. Where does that happen? Down here at the bottom. The coordinates of this point is 0, negative 1. What is the angle here at this point? This is 3 pi over 2. So our third solution, 3 pi over 2. Okay, that's it for today. Let me just leave this up for you guys so you can follow it through. That's it for today. Thank you very much.